Anyway. Hi, everyone. Thank you very much for inviting me. So I propose a short break away from turbulence. Well, people who know me are used to the fact that I never managed to be in the team on the festival. Um, so this is part of an ongoing work that I'm doing with a group led by Carl Lackner from IPP, with also a contribution from Justin Ball and with other colleagues from Paris. And this is about evaluating the startups, because there are lots of startups now who claim, well, they have a lot of claims, and we need to evaluate such claims. So maybe some of you have already done that, but we would want to dig maybe just a bit deeper. And so today I want to talk to you about the two startups doing FRC plasma. So FRC means field reverse configuration, and I will show you what plasmas are about. And they are helium and TIEAE. So the reason to focus about those two is well, the first FRC plasmas are quite interested from a pure plasma physics perspective, but also they are heavily funded, so they have both crossed the $1 billion of total funding. So we need to have some opinion on that, some educated guess about what they are doing. So I will mostly focus on helium, which is doing their scheme is about doing the adiabatic compression of FRC plasma. So it's a pulsed scheme. And I hope I'll have time also to talk about tri-alpha energy, also called TAE. Maybe you've heard about this one. And they plan to have a long-lived FRC, which looks more to maybe what we're used to. And first, I will introduce what FRC plasmas are. So on this picture, you can understand what the system looks like. It's actually a magnetized plasma that is fit within a solenoid or a theta pinch or a mirror-like configuration. But inside, you actually have a toroidal plasma, which because it has a purely colloidal field. So the way it was done historically is by having first a theta pinch, and the plasma will be relatively hot and hot enough to conserve its own flux. And then if you reverse the outside field, the magnetic field will be reversed, and what will happen is there will be reconnection between the outside and inside that will close the loop and create a toroidal configuration. And so I will make a drawing because I will need some quantities that I will come back to. So this is your solenoid. You have the external field like this, and you will have a toroidal plasma with purely colloidal field, no toroidal field, and of course the other side. Okay, and the field is reversed. This is why it's called reversed. And you have a separatrix, and this is called RC, the coil radius, and this is a separatrix radius, and then this is called the length L. Okay. And so you see, this is a toroidal plasma that fit inside a solenoid like magnetic field. And so it has unique features, in particular, the fact that you can easily compute the beta, the average beta. So the average pressure divided by the outside magnetic pressure to be related to the parameter XS, which I will use. So I also write here, which is the ratio between the separatrix radius and the coil radius. So you see that it's 1 minus 1/2 of XS squared. So XS is typically not so large. So you see that beta, the average beta will be between 1/2 and 1, and you can easily approach 1. And so this is of course interesting because it can use the magnetic field much more efficiently. But it also comes with the drawback that the confinement time tends to be very small in this kind of devices. And the reason is that you have some field nulls at the O point and X point. The field inside the configuration is quite low because of the large beta. And so typically you do not have mu conservation, for example. And so a particle that approaches this kind of points, they're easily lost. And so the confinement time of this kind of device is not only slow, but it's also a particle confinement time instead of an energy confinement time. It will be very important. for the discussion. Okay. So yeah, so the when you think it has low confinement time, you think, well, why even try? But since it has a high beta, and you can rewrite the triple product n t tau as being proportional to beta times tau, you think maybe you can compensate the low confinement time with the high beta. So this is something that we need to evaluate. And so now I will focus on the scheme of Helion. So Helion plans to use the deuterium helium-3 reaction, which is here. So one of the features of this reaction is that it produces only charged particles, and this is really essential to the scheme because this is they want all the particles to remain in the configuration to contribute to increasing the FRC energy balance to eventually recover the energy directly. So I will show you how. So if you look at the reactivity of deuterium helium-3, it's of course, as we know, it's lower than DT. But if you multiply the reactivity by the not the total fusion energy, but the fusion energy that comes out as charged particles, you get the green curve, and you see that it's shifted to the right, so you need to go to higher temperatures, but it's still quite high. And so it tells you that, well, we need to dig into the numbers. Of course, where does the helium-3 come from? It's the same kind of problem as tritium, and we don't have it. And so we need to make it, and they say they want to make it in a dedicated machine. So this is actually a big problem, but I will not talk about it. So how do they plan to actually make a reactor? They have this machine, which is long, and they make two FRCs. And when they make this FRC, they come out with a temperature of roughly 0.1 keV. And the nice thing about FRCs is that they're inside this solenoid. So if you start to increase the field here, there will be what they call peristaltic compression. It's like the toothpaste when you press a tube, and so they will move very fast. And you can extract them above Alpine speeds, and when they collide, there will be a thermal equilibration which heats the plasma to roughly 1 keV. But then you still need additional to do something additional to take this temperature to about 10 keV and probably several tens of keV. And so what they want to do is to have this extremely large coil. So you see it has a very large radius. It's a copper coil that will be ramped up very rapidly to increase the magnetic pressure, and the outside magnetic pressure which will compress the plasma both radially and axially. And they have already gotten results. I think they have already produced 8 keV with their previous machine, and now they have a new machine that will produce new results with a larger feature. Okay. So how do they plan to actually collect energy out of this? To understand this, you should see what happens from an outside operator as an LC circuit, where the solenoid is actually a variable inductance, where the inductance depends on the plasma state. Because you have a plasma here, it changes the relation between current and flux. And so when you are putting current in the coil, what you're doing, you are exchanging I deep side work with the generators, which are basically capacitor banks. And so the typical thermodynamical cycle looks like this in the relevant extensive variable psi, the flux, and intensive variable I, the current. You ramp the current up, it increases the flux, and then you have some fusion reactions that increase the energy in the plasma, and you see you move up, then you ramp down, and the area of this region will be the work that you can collect. And so this is why you need to have all the particles that come out as charged, because if they don't contribute to the energy balance, they are lost. Or then you need to do what we do in tokamak, to have outside blankets to collect the energy, which is then different, and then you have different rules for the cycle. So in principle, the efficiency of the cycle could be large because it's basically related to the ratio of temperatures between the compressed state and non-compressed state, and this ratio can be large. Okay, so what are their claims? You know, they made this figure in a recent paper, and which was the basis for my interest in that, because if you believe this curve, well, what is written on this curve is you have the temperature on the x-axis, and then you have some powers on the y-axis. So the black curve is the d helium-3 fusion power. Then this curve is the Bremsstrahlung. So it decreases with temperature because this is done at constant B, magnetic field. So when you increase temperature, you actually decrease the density, and the dependence in density of Bremsstrahlung is stronger than temperature. So when you increase temperature, you decrease density and you decrease Bremsstrahlung. And then you have this curve, the dashed line here, is the transport losses, which come from, as I say, an experimental scaling law. And so if you believe this curve, you find that above roughly 20 keV, with 20 Tesla, you could actually have a fusion power much larger than the total losses. And then you need to, you know, take this maybe seriously. But there's just, it's quite hard to believe, but we checked and rechecked and rechecked our calculation, but basically this curve is completely wrong. It's plain wrong. We have a big problem. So how did we try to reproduce? Basically, we tried to reverse engineer the curve, and I will show you the result. You've got to be careful with a few things. For example, when you write the pressure, you've got to be careful about the temperature ratio between electrons and ions. For example, in this figure, the ratio is 0.1. And it means they don't heat the electrons much compared to ions, which is really important because you see the ion temperature gets this factor here, the denominator. So if eta EI is small, it will make Ni larger. So it means if electrons are cold, you get more, you can put more ion density and so more fusion power. So this is actually very important that they can keep this ratio small. And they get this ratio small because of their merging method. Okay, and so then you write the fusion power. We all know what fusion power is. Reactivity, you just look at the tables, so you express in terms of B, beta, etc. The Bremsstrahlung also is very well known, and we have the same formula as they. I mean, there's no secret here. The secret lies in the geometrical factors that enter in the scaling law. Well, this epsilon is also an important quantity. It's actually not a small quantity. It's actually a large number, which is L, the length divided by 2 times the submatrix radius. And you see, basically, it's as in tokamaks, the larger the plasma, the more confinement you have. But they don't say in the paper what number they put here. And so we have to play with these numbers, but I will show you now. We try to reverse engineer the curve with the 2 sets of assumptions. One is what I call the realistic size assumption. You look at what they say the next machine called Polaris will look like, and basically it should have L, core radius, and XS in this kind of range. And it gives you this curve for the sum of Bremsstrahlung and transport. And if you take a very, very optimistic size assumption, like a total length of 10 meters, which of course is huge, not for the total machine. It would be the length. It would be the length of this section. Okay, so it's really huge. And a coil radius of 1 meter, meters in diameter. And excess also, they tend to exaggerate the size of excess also, so 0.5. But even with such optimistic size assumption at 20 Tesla, you're barely exceeds fusion power barely exceeds the loss power. If you want to be to have some margin in to go to 30 Tesla or 40 Tesla, but for an actual machine that looks like theirs, like Polaris, even at 50 Teslas, you would not exceed the loss power. So we're really puzzled with this result, like how they can get such wrong curves. So we have a few possible explanations, but it's hard to explain. So basically, if we really assume that that curve has 20 Teslas, their fusion cross sections are overestimated by factor of 10 for the fusion power, and the transport is underestimated by a factor of 10 to 100. It's hard to know exactly because they don't say the size precisely, but from what we can think. Okay, so then we don't. Yeah. Not too well. Okay, there is another important point because we could say, well, we don't know the size. How can we have a bit more systematic review of it? The FRCs, they have a stability criterion. They are typically stable over a period that is longer than Alpine times, and for reasons that are thought to be related to the large kinetic effect, because since an FRC has a large beta, it has a low field, and so it has large more radii. And so kinetic effects, which typically cannot stabilize an ideally unstable situation, well, in that case, they actually can. But it comes with a caveat. So it means the radius should still be not too large, because the larger the radius, the smaller rho star is. And if rho star is too small, the stabilization does not work. And also the criterion depends on elongation. So the more elongated the plasma is, the more stabilization you have. So unfortunately, we don't see here, but basically, if you plot the ignition criterion and stability criterion, the function of core radius and length, you find, so there's a boundary here that goes like this. And so the larger the plasma is, the more the closer you are to ignition. But for a given RC, you need to increase the length so the elongation to be able to stabilize. So you have the curve that goes like this. Maybe you see it on the screen there. And you can also, when you increase the size, you increase also the global magnetic energy in the system, which are the contour lines there. And so now you can ask for a given value of xs, which is this parameter. You vary the temperature and the magnetic field, and you ask what will be the requirement for the total magnetic energy injected in the system. Okay, and so you find this curve. So the more realistic case is the left, because excess at large compression should be roughly 0.3 or even less than that. And you see that in the range of parameters that you could hope to achieve, like between 20 and 30 keV, maybe if you're optimistic, and 20 to 30 Teslas, you see that the curve tells you that you have more than like a few dozens of gigajoules of magnetic energy injected, which means, the NIF has 400 megajoules of total capacitor bank. So if you count in terms of total number of NIF capacitor banks, it starts to add up quite a lot. So this is a big concern. Then there's okay, from a physical point of view, what I said so far is not very exciting. It's just putting numbers, like an engineering word. But there are also physical constraints that are quite interesting. In tokamak, you can have a very large Q because it's not a bulk system, and it has an energy confinement time, which is not a particle confinement time, it's an energy confinement time. So if you start to inject energy, you start to be in a burning phase. And so the Q goes to infinity when the confinement time reaches a loss of time. Okay? But in an FRC, the confinement time is a particle confinement time. And so it means that if you don't replenish the density, if you just rely on fusion energy to replenish energy, after the confinement time, the particles are lost. So no matter how much energy you put in the system, there's no plasma anymore. And so the capital Q then becomes typically the peak fusion power times the duration of the burn, which is fixed by the confinement time, divided by thermal energy, which is just P fused over P loss. And as we have seen, this number, actually, we think it can not exceed 1, but even if it does, it will just marginally exceed it. But Q cannot be very large. And so that means that the plasma energy at the end of the compression stage is of the same order of magnitude as the energy that you can expect to collect. But of course, it's a huge drawback because in a 10 keV plasma where you have a reaction that releases more than 10 mega electron volts, so a factor of 1,000 per particle, you would hope to have a capital Q of like in the 1,000 range or 100 to 1,000, but you can just have a few units. It means you are very inefficient at burning the fuel, and it has another consequence. So if you look at the ratio of plasma energy, so the energy that is thermal energy in the plasma compared to the total energy that is injected in the system. The problem is that when you start to compress the plasma, you do so by increasing the magnetic pressure outside, which shrinks the plasma. But you have to count all the energy that is in the outside region. So V squared over 2 naught times the volume. And you find that when you increase the field ratio, this drops quite dramatically. It's 10 to the -1 to the -2. Can visualize this in terms of field ratio or temperature ratio. And since we don't exactly know the starting point, it's hard to have different numbers. But if the plasma is 1 to 2 keV at the beginning of the compression, and you need to reach 20 to 30 keV, you need to be above this factor of 10 here. And you read the curves, it's roughly 10 to the -2. So it means the plasma thermal energy is in the range of 1% of the total injected energy. And so is the fusion energy that you want to take. So you run the current up, then say you inject 100 megajoules, you will have in the order of 1 megajoule of fusion energy that is increasing your plasma internal energy. Then you run the current down, and you must not lose, independently of the presence of a plasma, you cannot lose more than 1% of the injected energy. So in terms of quality factor of the LC circuit that is feeding your system, the efficiency should be larger than 99%, or you can put more precise numbers, but this is the range. And when you manipulate 1 millijoule, it's very easy to make a very, very large quality factor, in a tabletop small LC circuit. But when you manipulate megajoules or gigajoules, I strongly doubt it. Okay, then there's another crucial point. As I said, the curves of fusion power over loss power depend strongly on the ratio of temperature between TE and TI. Today, they observed in the plasmas that TI is much larger than TE, but of course, they don't stay like that for indefinitely because there is energy exchange at the collisional rate. And if you just take this collisional rate and you scale up to a reactor parameter, you find that the temperature equilibration will also kill your capital Q. So the capital Q is further decreased because you have a TE to TI equilibration, and of course it decreases TI, it decreases the fusion rate. So Karl Lackner computed that for even like at 40 keV, compared to the Q that you would have expected without this effect, it's reduced by a factor of 10. Okay, so another strong criticism. So for helium, the conclusion as follows. It's really hard to believe, but I encourage you to check the numbers. You will, when I first met Karl, he said that he had also similar conclusions and couldn't really believe, but the fact that I independently found the same things and rechecked and checked and checked, it seems like the curves are just plain wrong. Okay. And also the sizes required to obtain the quoted diffuse or different, they are prohibitive in terms of the total magnetic energy involved. And so Q will be limited to small values and further reduced due to PI equilibration. And so the quality factor of the cold system will also be prohibitively large. So for the helium, I leave you with that. I think you have the elements to make up your mind. How long did I talk? Can I still talk 5 minutes on PA? Yeah. So now I want to talk very shortly about Tri-Alpha Energy. So this company has been around also for for a longer time than helium, and they have completely different approach. So an essential feature of their scheme is that they want to go to steady state. And as I told you, the confinement time is the particle confinement time. So if you want to have a steady state FRC, you need to replenish the density. And this is done thanks to neutral beams. So neutral beams are really an essential feature of the device. And they have not just one role of particle replenishment, but four others. So of course they are heating the plasma. They also provide the kinetic stabilization, because as I said, in a FRC plasma, you need large Larmor radii. So with beams, you have larger Larmor radii and larger effect. They also provide a torque, actually there are two components to that. It's also the edge biasing that provides the torque to actually counter the natural tendency of FRCs to spin up. The FRCs tend to spin up in this direction, and it has it leads to a rotational instability that they need also to take into account. And they need to apply a torque actually to compensate this rotation. And this NBIs also provide some current drive, which would have the impact that they can now remove the pin-to-pinch formation method and be completely in a range where the FRC itself is created by the NBI, and they have managed that. They have put this in a Nature paper here, and so it allows you to reduce the size. Now you look more like a mirror. So what are the merits of this approach? Well, as I just said, this long-lived FRC is more like an improved mirror. So you see, it really looks like a mirror, but instead of having the usual mirror configuration at the core, you have a confined toroidal plasma that has a bit of confinement. And now the axial losses of the typical mirror, now they will, instead of being driven by the whole plasma, they are driven by a small layer on the outside. So it should reduce the axial losses compared to a mirror. And it means that, when you play with the mirrors, you need a lot of tricks to improve the confinement, like end plugs, which they have, by the way, or non-active symmetry coils, edge biasing. End plugs are the end mirrors for attendant mirrors. Thermal barriers, splashing. They have all sorts of tricks, to improve the confinement. So now you could say, well, with the FRC, we need less of the tricks of the mirror. So I think this has some merit, because the FRC can be seen as such a trick. Okay. So we do not have like a definite opinion on TIE now, but what I want to briefly show is that there are some constraints related to this need of beams that also quite strongly limit the Q that you can achieve. So this is a work that was done by Justin Ball from EPFL. Well, it's not published to create no, but I think it's quite smart. So for stability, you need some amount of energy in your plasma to be in the form of the beam. And it seems to be about 40% according to experiments. So you need to have 40% of the energy of your plasma to be in the form of the beams. And so it means that you should have some ratio between the energy in the beams and in the thermal energy that's larger than 2/3. And because it introduces some dynamics associated to the slowing down of the NBI particles. And actually, when you use this and you compute, it helps you to find the density ratio between the different components of the plasma, thermal species and the NBI. And so when you compute the capital Q, which will be the sum of the fusion power, so the thermal component of the fusion power and the beam target component divided by the total NBI power, you find expressions that are easy to manipulate and that can be plotted so here you have T temperature and in terms of the NBI energy. And this is done actually with even very optimistic approximations for for the reactivity of the beam target part, which is just set to the maximum possible. And what you find on this curve that it's that for GT for NB equals NT or in thermal part, and you have a beam of deuterium. If you want to reach Q equals 10, you would need to be at 20 or 30 keV, okay? But you would need an energy in the NBIs of roughly about 2 MeV. And I think the guys involved with tokamaks know how challenging getting very high energy beams is. Yes?
Can you ask a very nice question?
Yeah.
This law, what is actually bold and which part is the extrapolation?
In this plot?
Yes.
Oh, this is very basic physics.
No, I just want to know which part is the extrapolation and which energy has been actually experiment done. And which
Okay.
part is the
I see. Okay, in their device, in their devices, I don't know. I think they have a few, normal, usual NBIs with a few, roughly 100 keV. So, ITER is planning to go to 1 MeV, which is yeah. Also, the temperature must be above 10 keV. Okay? It's just like there are some assumptions in this plot, but it tells you that if you want to go to Q equals 10, because Q equals 1 is not sufficient.
I understand that. I'm just trying to see which part is experimentally low and which part is the extrapolation.
Well, I would say
is somewhat low.
Yeah, I mean, we can have NBIs at 100 keV, yeah, but they have not, of course, they have not reached this part of the diagram because they have not reached 10 keV yet.
I see.
And I did not mention also, but they say they want to go to proton boron, not DT. And this is the next, of course, everyone knows proton boron has extremely low reactivity. So if you do the same plot but for proton boron, even at completely unrealistic values, you never reach Q plus 1, of course. So yeah, we don't really know what they say about so what I'm just trying to say that this requirement of having a lot of energy in the beams sets constraints to the capital Q. Okay, so I will stop here. So the conclusion is so that the set is set constraint to capital Q, and it will be hard to achieve Q larger than 1. Another remark also, which I didn't talk about, is that their plasma, so well, I briefly mentioned they need to apply a torque using edge biasing electrodes to counteract the natural torque and the spin up of their FRCs. But the problem is when you start to run this, to scale this up to reactor, there's an electrical consumption associated to the dissipation of trying to drive an electric field. According to Carl Wagner, it may also be prohibitive reactor parameters. So we're trying to address this. Okay, so that's all for me.